Alright, looks like we're live. Live somewhere at least. Duco's already walking around. I think he's gonna jump for the rack. Cool, looks like we're streaming on the YouTubes. Are we streaming on the Twitches? It's harder to tell over here. Looks like we are live on Twitch as well. Well, welcome back to the stream, folks. Sorry the streams have not been super regular lately. I've been in this kind of antisocial mood where I just want to write code, and it's had some good results, but it's meant that I've been recording less video. Anyway, I think that sort of tunnel that I've been in might be coming to a close, and so this stream is kind of my opportunity to talk about this milestone and to show you what we have and how it works. And then the next stream, or two or three will relate to the pile of stuff on my desk. So, where's me? There's me, but I want to show you Tuco also. Do I really not have a layout for just Tuco and I together? Let's just add a webcam to this layout. One moment. Hi, that's too big. Alright, that's kind of better. We can focus on Tuco, and I can be tiny and in the corner. Yeah, that seems fine. So, I've been working on this project lately, which some of you might know about. I've certainly been obsessing about it on these streams a bunch. But, yeah, it's basically a port slash kind of HD remix, or whatever you want to call it, of a game that I liked as a kid called Robot Odyssey. And so, this is a game from 1984 or so about digital logic, where you go through some tutorials and learn some about logic, and then the bulk of the game is this kind of classic adventure-style adventure game where you walk around and pick up items and build circuits and make your way out of this kind of Robotropolis zone that you're stuck in. So it was kind of a favorite of mine as a kid. I played it, I don't know how old I was, but probably in the neighborhood of like 10 years old or something. So it was after the game was like brand new. It was, it was released, like when I was probably way too young to play it, but I encountered it when I was a little bit older than that and played it on the DOS PC that my dad had. What I didn't know at the time was that the game was actually originally for Apple II, and the DOS version was a port of that. So I'd kind of become attached to the DOS version and took it upon myself in like 2009 or so to make this weird static binary translator that could convert that game's binary code, the actual 16-bit x86 machine code that shipped in the DOS version. It would convert that via a pile of Python scripts into C++. And my idea at the time was that I could turn this into a Nintendo DS game. And I wanted people to have a handheld experience where they could just play Robot Odyssey on the bus or something. And this project that I took on, what is it, like a couple months ago at this point, was sort of a revival of that thing from 2009 where I was porting it to DS. And this time I'm porting it to the modern web so that you can run it on desktops or laptops or tablets or phones. That last move just made it wobble more. I didn't need to do that. Okay. A little close to that panel of audio stuff there. Alright. So anyway, I mentioned that I was kind of binging on this project, trying to get it to a particular milestone, and I think a lot of times I undertake something like this and I just really can't leave it alone until it's got at least a minimum set of functionality that, you know, such that I can like at least walk away from it for a little while and not feel disappointed in it somehow. And there were a bunch of factors for that with this game, but I think the big milestone that I completed recently was getting it to have built-in support for managing saved games and saved labs and saved chip designs. So now you can actually play it in a browser and it'll save your work, and you can import and export those files. It's all serverless, which means that after you grab the initial like HTML and JavaScript and stuff from the server, there's no actual API, there's no communication with the server, so your game is actually stored locally in the browser. I should get something to drink because my throat is all scratchy, but I'll be right back, and then maybe we can actually just take a bit of a tour through the state of the current game, and then I can show you the code for a bit. And hello folks in chat. Got Christian Iverson and CRC Elite, I guess, in YouTube chat who say hello. A couple of folks in Twitch too. Hello. I'll be right back. Alright, got some tea. Tea is always helpful. And hello, Joseph and James. Nice to see everyone. Alright. So let's try the game playing experience here. So if you open a browser, I guess I already had a browser open to the code here, but so if you go to Robot Odyssey Online, you get the classic splash screen. And that splash screen should pretty much always show up immediately. It only needs like 20 kilobytes to download for that splash screen. I'm pretty happy with that part. And then once you get to the menu, this set of controls should also appear down here. So on a desktop machine, this is not amazingly useful. Sometimes the virtual joystick is kind of helpful, but you've got touch buttons for keyboard keys, which are really useful on mobile devices that don't have a keyboard. You've got arrow keys, they're sort of the full strength arrows, and then the dotted arrows for the large and the small steps. And the dotted arrows correspond to like shift and arrow on the keyboard. There's also a couple of controls down here that might eventually move into an options menu, but right now they're down here. There's a speed control and a palette selector. So you can select between the rewired palette or Apple II or DOS style colors. I think the gamma on this monitor is kind of low. That looks really dark to my eyes, but on some devices that actually looks like really bright. I think it's maybe one of those kind of indeterminate grays. Oh yeah, James is wondering if I'm like animating the menu entry highlight. Yeah. So I think I went over this a bit on a previous stream, but this menu is now completely re-implemented in HTML and JavaScript and CSS. So yeah, so like originally, if you pull up this game on the Apple II or in DOSBox, I mean, part of the reason I did this in the first place is that the game, while you can run it in an Apple II emulator, I find that kind of slow and annoying, having grown up with the slightly speedier gameplay on the DOS version. But the DOS version is really annoying to get running in DOSBox. I made a bunch of binary patches for that ages ago, but nobody seems to care. They just host the broken version in DOSBox, and it's like kind of annoying. Like the game supports only like very particular like XT keyboard scan codes, and if you use the keyboard in DOSBox, it usually doesn't send scan codes that the game can deal with. There's also a copy protection scheme that originally applied to the 5¼ inch discs, and if you don't patch that, then the soldering iron doesn't work in the game. So anyway, a brief aside about emulation and how it hasn't been great for this game. But yeah, this was originally part of the game. It was a separate exe file, menu.exe, and in fact, menu.exe no longer really exists in its current form in the translated version. There's a translated version of the cutscene, like the intro animation, that was part of that menu binary, but that's actually now, I moved it to a completely different exe file, and this is actually all done in JavaScript and HTML. I can do a brief tour of under the hood in a bit, but I think first I just want to go through the kind of exterior experience. So then there's, speed selector. 200x is kind of pushing the CPU performance, but it works pretty well. So yeah, then you can also just use the top section here and ignore the stuff below the fold if you don't need the controls here. It also supports joysticks. Whoops. Yes. So this is just an Xbox controller. It uses the HTML joystick API, so you might have to press a button to get it to recognize the joystick, but after that you should be able to navigate the menus with it. And then, okay, then this is the new file manager. So actually let's start a private window here, because you won't see the file manager if it's your first time visiting the site. If it's your first time, then you can just use the controls here, and you can pick one of the training sessions here if you're the type to go through the tutorials. If you want to just jump right into the game, you can hit this, and it plays the intro animation. And this is running binary translated code. So I do have a program that unpacks this entire data file now and repacks it just using the files that the cutscene needs. And then I have a binary translated 16-bit program that actually contains just the cutscene portion. So the menu and the splash screen are HTML, CSS, JavaScript. The cutscene and the rest of the game are running inside the binary translated environment. So then you can move around in here. There's a few button mappings here. There is not yet a system for redefining the button mappings, so if the button mappings that I've arbitrarily set up don't happen to work for you, then there isn't really a good way to change them. That's, kind of a nice enhancement that would be cool to add in the future, is a remapping system. But yeah, so you can use the game using fairly original joystick controls here. You can walk inside. Oops. You're supposed to be able to open that and then it stays open. It's just sometimes it actually registers twice. So yeah, and you can wander around. This isn't going to be a Let's Play, so I'm not going to go really far into this, but I'm going to hit by the Dalek. But yeah, and then you can go back to the menu. There's a button mapping for escape, but you can also press escape on the keyboard or use the on-screen keyboard to press escape. And then that goes back here. I also could have pressed S to save that. So let's try the lab. First time in the lab, it just goes right here. But if I do something that's really cool, let's say I put checkers in this room and I want to save that, I can press S. And then this could use some polish. It'd be nice if it actually showed you the same little view that you get for the file in the browser. But right now I just have a pretty generic success message when something saves properly. So you can click the modal to just dismiss it. Keep going. You can press escape and go back to the menu. So now I've got some stuff saved. Next time, so now if I click Robotropolis, I get this browser. And I've got a bunch of autosaves here. Those are the same saves that end up in your URL bar. So you might have noticed that as you're walking around here, if you leave it alone for a half a second or so, the URL changes. And in fact, you can use your browser history to navigate these autosaves and go back and forth. And if you make a mistake, you can like really quickly go back through the last couple autosaves to revert it, that kind of thing. You can also copy and paste these URLs to a friend if you're working on the game with a buddy. They're also usually short enough to fit into Twitter's URL shortener, so you can tweet them. And as I said, this is serverless, so this is actually the entire save game, with special care to compress it very, very tightly. But yeah, this is the entire save game. That's the same format that if you go to the file browser, you'll see these files that are GSVZ. So the original game save file format was GSV. That's unchanged from the DOS port. So if you have save files that you've been playing in DOSBox or whatever, or on a physical XT machine or whatever, you can get those files onto a modern computer and drag and drop them onto the web browser, and you can resume those files. In fact, I have some that we can do that with. Let's see. Yeah, so I've actually got some really old save files here. So I can actually just grab all those and drag them here. And as soon as you go over the web browser with your drag and drop, you get this little message that reminds you of what save file formats are supported. You can also drag directories and zip files directly here. So then it mentions which files it found. Let's try dragging an entire directory too. So here's chips. Yeah, look at all that stuff. Right. So the CSV files are saved chips. The LSV files are saved labs. I thought I had more labs in this directory. Oh, this goes with the cycler 4, but it doesn't have that in the file name. There's not yet a way to rename files inside this UI. That would be a nice improvement. But right now the names are just whatever you uploaded them as, or if you save them. So for example, if I go back to the game here, and so the autosaves just have date stamps, but then if I use the explicit save here, then you can see the file name here indicates what world you were in, which is better than nothing, but it would also be a nice enhancement for this to give you a way to enter a file name optionally, or just dismiss it without entering a file name. So yeah, so this is a nice old save file, and I can just resume it and keep going. So yeah, I've also just been making little tweaks to the controls, and like I think the mouse and the joystick should both be more usable now. The mouse still kind of glitches out the discotheque portion of the game, but the discotheque was never good anyway. So whatever. I should probably file a GitHub issue for that. So yeah, I mentioned this game, I feel like it's pretty much usable to the point where, you know, I wouldn't feel bad recommending people to start playing it if, you know, like if you want to play Robot Odyssey, this is probably the best way to do it right now. And you can do it on your desktop or your phone or your tablet. And yeah, it generally seems to work all right. And you can, you know, your data's yours. You can, while you're in the file browser here, you can hit export, and then it gives you a zip file. And the zip file, if you look inside, just has all the same files. And so likewise, it's compatible in both directions. If you save a game in here by pressing escape and S, it'll give you one of the full-size, like, non-compressed game saves. So like this one, Robotropolis World 2. And if you bring this file to a DOS computer running this game, you should be able to open it. I haven't actually tested that, but I haven't made any changes to the format, so And then these little ones here are chips, also in the original format. CSV stands for chip save, not comma separated value here. And then GSVZ is the original format, but then wrapped in a compression layer, which we could talk about the compression, but we don't need to. And then the thumbnails here are actually generated when the dialog box opens. So all the files are stored in IndexedDB, which is a relatively new browser technology that lets you, as the name might implies, have indexes, but what the name doesn't say is that it's sort of a persistent object store for your browser. So you can store sort of any serializable JavaScript object into a database, effectively, that ends up getting persisted to disk. And websites are allowed to store potentially large amounts of data this way. So I actually had a bug where each saved game, which should have been just like a kilobyte, was actually getting a copy of the entire WebAssembly memory region, which is 16 megabytes. And so quickly my IndexedDB was just getting to be hundreds of megabytes or gigabytes. And it was handling that just fine. It was getting a little slow. That's how I noticed there was a problem. But now that I fixed that problem, it's quite speedy. It's been slowest on, like on a tablet. This is like an old iPad. It's like, not an iOS 9 iPad, because those actually will not run WebAssembly, but it's just new enough to be 64-bit, but old enough to be a little slow. And that's like slow enough that you wait a little bit of time for the IndexedDB records to come back, but it's still not so bad. Anyway, yeah, like on a desktop it populates pretty fast. All right, well that's like all the basics for the port, I think. I could like briefly show how it works on tablet. I think I've got a way to broadcast video from this tablet, but I think that both slows it down a lot because it's already not a fast tablet, and it also kind of misses the experience of actually putting your finger on it. Alright, so if you reload this, pretty much instantly you get the splash screen here. If you just like tap this, it was actually still loading the WebAssembly, but if you are faster than it, it gives you a little spinner. If I was a little slower, then I don't think it would have even given me that spinner. So you can navigate by tapping, you can switch rooms by kind of tapping right at the doorway. It's not pathfinding or anything, so if there's an obstacle in the way, it'll just kind of move in that direction until it can't move anymore. So if I actually want to like do what it's telling me to do, I can press T to summon the toolbox, then drop the toolbox and open it. You can also navigate with this little on-screen joystick. For like making circuits, I find this a little bit nicer. If you long press, it activates the button also. So instead of just moving, you can use that to grab objects. So yeah, we could go through the tutorials, go back to the menu. If I hit Innovation Lab, here's all the saved stuff on here. So it takes it a bit to load these out of IndexedDB. And then they start rendering. I think the bottleneck here is the database, not the thumbnail rendering. Because if the thumbnail rendering was the bottleneck, that happens on the main UI thread, so you'd see it bog down everything. It would obviously be nicer to render the thumbnails on the background thread, but the problem with that is I don't necessarily want to run the entire game on another thread. And if I need a copy of the game engine on 2 threads, then I have to load it twice, which is actually pretty bad in terms of performance. That's weird. For a sec there, it had decided that I was trying to scroll the outer modal frame instead of the stuff inside the modal. Anyway, loads pretty fast. Crank up the speed a little bit. There's 2x, 4x, 8x, 15x, 80x. Yeah, like, it's keeping up alright, even running the game engine at 80x full speed. There's some weird glitches on the bottom of the canvas there. Is that a GPU bug? Pick a color scheme. CGA colors. Yeah, and then file import and export should work all right here too. So go here, export all, prepares a zip file. Just takes a little while, and then gives you a little pop-up. And then this experience is coming from a library I'm using called Download.js. And so it looks a little different on each platform, but it basically makes a blob, like an in-memory object in your browser, and then opens that in a different window, triggering a download. So then you can open this in your local file manager. So I think this is going to go to my Dropbox or something. Yeah, it's just like giving me a file manager and a bunch of places to save it. So like, for example, that file name, I don't know why we're stuck with unknown on iOS. If you save this on desktop, it has a nice name with a timestamp and stuff. But you can save that in your Dropbox or your local files, your iCloud or whatever. And then you can load files in a similar way. Like file import. And then it's going to ask if you want to take a photo or go to your photo library, because I guess this whole experience is kind of centered around images. But you can also just hit browse, and I think that'll open a file manager. Yeah, it just opened my Dropbox, and I think you can also choose like your iCloud drive or the stuff that's on your iPad. So, yeah. There's a bunch of autosaves. I'm sure I'll want a system for managing the autosaves a little better at some point. But right now, you can basically just scroll through the thumbnails. This is like the slowest device I've been testing this on. Yeah, and there's currently no way to zoom into the thumbnails on mobile. On desktop you can hover and they'll get bigger. I think ideally there'd probably be some experience where you can tap the save game and get details about it without just loading it right away, but right now when you tap it, it loads it. think this delay is probably it running a bunch of JIT compilation on the game, but I'm not actually sure why we're waiting right here. Because the engine should be loaded. And like we were just doing a bunch of thumbnails, which should exercise the same code paths as starting the game. Huh. Well, that's a bug. I don't know what just happened there. I could attach Safari over USB to debug it, but I don't really feel like debugging that right now. I might have also like run out of memory or something. I mean, loading in general works. I think there was just something going wrong right then, so I don't know what conditions actually caused it to break. Anyway. Yeah. You can also use joysticks on mobile devices, which is pretty cool. Let's see if I have this set up. Oh. Where did I leave that remote? Alright, so like first of all, the standards situation with HTML Gamepad API is still not amazing. The API seems to basically work on all the major browsers, but the button mapping is all over the place. Oh, it looks like we're working though. So I actually have a special case for this particular joystick because it, for some reason, the mapping has the y-axis reversed, and I think it was showing up differently on different browsers, but I was getting into a situation where I have two devices, one of which claims to have a standard mapping and the other of which doesn't, and the standard device has some buttons on it, but all the axes are on the non-standard device. But, yeah. And save chips. Load chips. So many chips. Yeah, if you never tap any of the buttons, sound will be muted because mobile Safari only lets you create an audio context if you've had certain qualifying user interactive events, of which gamepad interactions don't count. There we go. Yeah, I've tried to map the shoulder buttons to cursor and soldering iron if you have those. I still don't especially like the experience of soldering with the joystick though. I think mouse is the best way to solder, but joystick is certainly better than on-screen arrow keys. And I think the physical joystick is nicer than the on-screen joystick, although they're both alright. I don't have a joystick mapping for fast forward yet, but there is a fast forward button down here, which you can actually just kind of keep tapping. How does the paintbrush tool feel with this? Because I could actually make this continue. Oh gosh. Really, you don't want to run the paintbrush tool at too high a fast forward speed. Most of the controls get really hard to run if you're fast forwarding really fast. I mean, I included those options mostly because if you're testing a circuit and you want to see what it looks like after it runs for a while, it's nice to be able to just let it do its thing. Let's make a little cell for this robot. It's 200x, or at least it's trying to be. Whoops. The mouse controls are a little easier. You can get more of a sense for how fast the battery drains. It's not that fast, but like it will drain eventually. And there it goes. Alright, well, let's take a little tour through the code maybe, and then that's pretty much all I had planned for this stream. Let me know if anybody has questions, or especially if you want to see like how I did a particular part of this, or like a focus for the code walkthrough. But I think I mostly just wanted to show the storage-oriented parts of this, because that's mostly what I was working on recently. We can get a better view of Tuco also. Computer vision does a great job of noticing Tuco even from that angle. Alright, so I don't know, one way that I like to, look at what's going on is through the lens of a debugger. So if we just look at, what's going on when this site loads, like I haven't been setting up a lot of, like I haven't been setting up a debug build, for example. I've been just like using this as an excuse to practice debugging minified JavaScript, and it's actually been pretty alright. Like the current debug tools in, like all the browsers really, I've been testing this a lot in Chrome, Firefox, and Safari, and they all have pretty good debuggers, especially Chrome and Firefox both. Anyway, I wanted to monitor the network resources here as we load the site. Okay, so the very first thing that happens, we get this index.html the index HTML by itself is actually enough to draw the whole splash screen animation. That has the images and CSS inlined in it, and it's like 30 kilobytes or something. Yeah, in fact, if we just open this in the preview, you can see the animation running, and it just stops right there. Like, that's the whole site, but it's got all the scaffolding for everything else we add later. So we've got a bunch of these long lines here which were added during build. This has links to the icon resources. It gives up on syntax highlighting this line at some point. And then there's the inlined CSS, which also has an inlined font. It's a very small font, but it's that the one that I generated from the game's in-game font during build. Some of those data URLs end up getting loaded right away. So these were inside that HTML. So we've got these splash screen images. These get unpacked from the game's data files during build and turned into PNGs, which are then included in the index HTML. And the menu is sliced into pieces so that we can put them on separate elements easily. This is the cursor. It's got all this extra space below it because that's like the format that it was in the game. This is just an overlay that goes over the screen, and it highlights the first item, and then we can shift it down. So like I could crop it, but then it would be harder to get the aspect ratio right. And then this is the actual WebAssembly. So this is like 1.4 megs uncompressed. How big is it compressed? Do we not have a content length in here? Anyway, this is claiming the engine compresses down to 360 kilobytes, which is pretty rad. This file contains all the C++ code, as well as all of the binary translated code from the original game, the stuff that we need at least. There's a lot of stuff that we ended up replacing with C++ code, or HTML or whatever. And it includes, like tiny emulated file system and DOS nuggets that the original game calls into. It also includes like a queuing system for output. And it calls back into JavaScript to actually render graphics and sound. We got icons. So then at this point, the service worker loads, and this script is entirely stuff that was generated by a package called the Webpack Offline plugin. And so this actually has, can we not clean up this code here? If we go to sources over here, we can see that code, but with some pretty printing. This will download all of the application files in the background, and it'll maintain a cache, which it can update. So this is a pretty awesome plugin. Basically, the first time you visit the site, it'll download a snapshot of the current version of all the resources here. So it's a little annoying that this includes a bunch of icon sizes that you don't necessarily need. I'd like to find a solution to that. But for the most part, this is working as I intend it to, where it lists the resources that comprise the game. In the background, after the game has actually started loading, it'll start downloading them in the background and caching them. Likewise, if you revisit the site, the service worker's cache actually immediately lets you load the game without even having to go out to the network. But then in the background, the service worker starts checking for updates, and if there's a new version of the site, it'll create a new version of the cache, and then next time you kind of reopen the site fresh, it'll actually be switched to the new version. So it's kind of like a nice application package upgrade story for web apps. I can see maybe wanting to do more complicated things with the service worker later that would require me to get in this code myself, but right now I'm just using this Webpack Offline plugin, and it's pretty great. So yeah, that's what this is. The service worker starts, and then it starts downloading a bunch of resources. And then that's pretty much it. Everything else happens There should also be a palette image. Where is that? Oh, that's this one, yeah. Rewired tile set. This is the rewired tile set is the default color scheme. This one. The other color schemes are generated with code, so they don't have images necessarily. Oh yeah, good question. Weebrew Lover is asking how I did do the binary translation. Yeah, no, that's a great question. That was kind of like the genesis of this project was like, well, I wanted to make my own port of this thing, and the like sunk cost fallacy that continued the project after the point where I'd already dumped tons of effort into it was the binary translation layer. So yeah, actually it might be fun to just do a clean build. I can show you what the build process is like. Alright, so we've got a makefile, which initiates the whole process. I could move more of this to Webpack. Right now there's kind of a weird division of labor between the Webpack side and the makefile side. The makefile is my kind of overall build system, but a lot of the stuff is done by Webpack, like generating icons, HTML templates, obviously packing all the JavaScript, and doing like running Babel to translate stuff into ES5. Ready to go. But a few things are still done in this makefile before any of that starts. Most notably, building the WebAssembly. Oh, wait, is that where you want to sit today? That's cool. Oh, why are we so wobbly today? This corner winch is having a little trouble keeping up. The winch is just, or the bot is just really hard to drive in this far corner. Think about ways to make that better. This is a pretty good view on this camera, actually. So yeah, the binary translation is all done by a bunch of Python scripts at build time. So the first step is it needs a copy of the original game. And so I've just been using a zip file that has a copy of the DOS version. You can get this online from a bunch of different places. You could copy it off of 5 1/4 inch discs if you've got those laying around. There's a script that will verify the SHA-1 hash of all the files in order to make sure that we're dealing with the right version. But if you have 1.1, which is the latest DOS release, then that should be the right one. And so it'll go through and check the files and put them in the right places. It runs a bunch of kind of asset preparation scripts where it'll take apart the game's sorry, I'm trying to say too many things at once. There are a bunch of graphics actually included in the exe files. But there's also a separate file with the .shw, like show extension, and it's just a list of compressed frames that are used for the cutscenes, but also for the main menu. So there's a whole step where I unpack those. That's where those images that end up in the index.html come from. And then I repack them using only the files that are necessary for the cutscene, and then edit the corresponding exe files during binary translation so that they match. Oh, this cat. Alright, so I actually need a quick restroom break, but I'll be right back. Don't go anywhere. Let's do a build. Okay, and I'm gonna actually go through the output a little bit slower. So the first thing it runs is this check originals script, which looks for the files that we're trying to find, looks for them by hash, and then puts them in the right locations according to a mapping that's in this script. Then sbt86 is my little binary translator. So you can see we're running this bt game script, and then giving it the build directory. And then it's going through and finding a bunch of specific locations in this binary that it wants to modify. Oh, hey, Tuco, leave that alone. Let's take a look at that script. Tuco. No, honey. Oh, you want to play with this stuff. No. Okay, BT game. So, oh gosh, I really need to change this color scheme because the comments have got to be invisible on the screen right now. What is actually readable on the video screen? I'm thinking maybe this one. Gosh, every time Tuco is exploring my desk, he wants to get into stuff he shouldn't be. Sorry. Oh, Tuco, you're not gonna leave my desk to explore the trash can, are you? Oh, honey. Here if you want to, but... Are you gonna explore the heater? Tuco, what do you want that's in there? I think he wants the packing peanut, but I'm worried he's going to be interested in the bits of desoldering braid that I put in there too. honey. Oh, dude. Oh no, James says the original color scheme was better than this one. Alright, we can try switching it back. Is this any better? Where does Tuco keep going? Oh, now he's over there. Let's try this one. I kind of like this better. So, fundamentally what this is doing is it's making a series of modifications to an in-memory exe file, and then it's unleashing a translator that descends literally upon the entry point and starts generating subroutines. So, it's invoking a bunch of patches that are in this common Python module because they're common to several different exe files. But for the most part, what this is doing is it's opening this DOS binary, patching it, and then writing the code to file. And in this case, it's writing this C++ file and this class. So then why is it patching it? Well, there's comments explaining most of these. So there's a bunch of things that we import from this other file, which will have their own comments. Some of these are replacing a bit of original code with a bit of C code by substituting the original instruction with return, and then kind of decorating that address with an additional chunk of C++ code. So for example, this thing that says world file load failure, we could actually find that in the output over here. Right there. This is kind of ugly code, but... So this ret turns into goToRet, but then before the code the translator generates, we end up with this assert. But yeah, this is like what the code looks like. It's not pretty, but it generates all right WebAssembly code. Not the best, not the worst. If you were to just directly turn this into JavaScript, it would not be good. You really need this to go through an optimizer. This is not being produced by any sort of a compiler, really. It's more like a macro substitution device, which looks for mappings from different kinds of instructions to C++ code. It understands like addressing modes and stuff a little bit. This relies on a lot of assumptions about the original code. We don't actually emulate an x86 stack at all. The stack is completely kind of higher level emulated. So we translate subroutines one at a time, and then calls between subroutines turn into invocations of a different C++ function. So like this is a C++ function, which you can think of this as being equivalent to an original code function that was at this address. But that's not strictly true. It's more like, here is all the code that was reachable from that location if you don't follow calls. So any unconditional or conditional jumps to other code will cause that code to get included in this subroutine. So there are some cases where you can end up with, like for example, if you have code that calls two different entry points, and then those two entry points do some stuff, and then they have unconditional jumps to a third common location, that code will end up getting inlined effectively into those two separate call sites. So you see that sometimes, but it doesn't seem like that's causing a huge amount of code duplication, but it would be interesting to quantify that. But yeah, it's like a subroutine at a time binary translator. And then the kinds of things we're using is to patch include what? So I'm like, these are just like modifications to the game's control flow. So changing the error handlers, moving around some modal dialogues. I can't let the game just continue to run forever. You actually have to just call into it and then be able to get control flow back at some point and then give that back to the browser. Even if I could run the game on a background thread, which has its own problems, I couldn't let that thread run without any interruptions because I would not be able to receive any incoming messages then. So Emscripten, which is the compiler backend that generates the WebAssembly here, Emscripten has its own solution to this problem where it's sort of this additional layer of emulation for the control flow that gets added so that you can kind of abort and then resume executing the original code from a particular location. But that's actually been really challenging for me here. In the Nintendo DS version of this, I had the luxury of just being able to write like low-level C++ code that did stuff with the stack if I wanted to. So I had something which set up a separate stack that I would run the original like translated code on. And then when I wanted to interrupt the translated code, I can just long jump out of that stack back onto the original stack. So I can't do that in WebAssembly because you can't modify the stack. I do still use long jump for this, but just to break out of the interior, once I've set a continuation callback, so it goes over here now. And Emscripten gives you an emulated set jump long jump, but you can't use that to switch stacks entirely like I was doing before. Oh, that's a funny question. James is wondering if I did this binary translation stuff before or after working at VMware. Yeah, I think I started this as a side project while I was working there, but it wasn't really influenced by the stuff I was working on at work. Because I didn't work on this binary translation stuff at all at VMware. I was working on device emulation. But yeah, I mean, I had like a bunch of side projects that was just like how I always operate, and you know. But yeah, no, this was kind of overlapping, but I think part of the reason I liked working on it was that it was just like so different from the kind of translation or emulation that we would have done at VMware. Yeah, it's like weird the kind of overlap that I had with like personal and professional projects sometimes. It's like I was working on USB in my personal life since way before I started working at VMware, but then I learned a lot working on it there, and ended up doing some stuff there that I probably wouldn't have cared to do on my own. But yeah, it's like my experiences now are certainly a mixture of stuff that I learned just on personal projects and stuff that I learned working on virtual devices. So yeah, that's what this stuff here, the control flow breaking. So it's actually taking some location where we can break control flow, and in fact we need to because there's a loop that's just waiting for keyboard input. And it'll add a delay to this output queue, which is how we keep track of things that need to go on the screen or come out the speakers. And then this continue from will actually throw an exception to jump out of the translated code and set a callback. This R here is actually a snapshot of the machine's registers, the emulated machine's registers at this point. So it's actually just copying that and the continuation to some internal location in the process here so that it knows where to continue on the next invocation. And so these don't necessarily correlate with main loop cycles. There's another layer where we want to run the game until it produces like a frame, usually, or until it gives you a delay. So we just re-enter the game until the output queue has a non-zero amount of delay in it, and then we're done. And then we tell JavaScript we want to call back after that delay. Oh yeah, interesting. So yeah, Christian was also saying that the light gray on white was looking pretty bad with the video compression. Yeah, it's like kind of frustrating the compression and text interactions sometimes. So yeah, like all of this is just kind of making adjustments to the control flow specifically in this binary. Whoa, Tuco. Oh, Tuco. Funny, the first compiler I wrote was like way before working at VMware. I think it was in some like high school C class, because I think there were a couple of programming classes. Which high school was this? Yeah, I think it was like a basic introductory programming class, and then there was like a C programming class, but they were both taught by math teachers. The basic one, I remember a lot of people making like text adventure games. I think it was like, you know, input strings, print strings, if statements, stuff like that. And there was a C class. Yeah, I was getting distracted thinking about the project I did for that basic class, which was also kind of funny. But yeah, I think for the C class, I think I made like a little compiler. You could give it code in kind of a Forth-like language, and it would generate code. I forget whether it did any optimization. Like, it might have done constant folding or really basic stuff like that, but it was mostly just generating code. Like, it was basically a parser tokenizer, a really simple code generator, and a really simple linker. The teacher didn't understand any of it. He just gave me an A. You wanna go? Alright, yeah, then this stuff is a bit more just like common to everything. Video memory stuff. There's the copy protection. So yeah, this mostly works by finding machine code sequences that contain wildcards in it. So a lot of these are fragments of assembly code that were compiled and linked into multiple binaries. So it's the same instructions, just with different addresses for some of the parameters. So that's what I'm looking for here. This find code is specifically looking for one instance, and it'll throw an assert if it finds 0 instances or it finds more than one. Whereas some of these were actually looking for a list of matches. We're also looking for addresses that we can publish. So this is actually looking for a sequence in the data segment that we can use to identify the robot data, the grabber data, circuit data, world data. The world data is actually identified by finding the address in some code that accesses it. So we're looking for an address in the binary. This returns an address object. Then we're reading from that address object. This is just a 16-bit pointer. And then we're also reading, because I think this is the address of a pointer to the world data, whereas we actually just want the address of the world data, so we're dereferencing the pointer. Yeah, this is how we catch video output. So an earlier version of this emulated the CGA, CGA graphics frame buffer for the whole game, But now the game is actually rendering using higher level patches, which we'll see below. And this method is only used for emulating frame buffer access during the cutscenes. So this is actually adding memory trace. So it's looking for writes to this segment, and then when the trace fires, this is the code that gets run. And these are just constants we're substituting into the code. So this is then like kind of dividing it, so we're only looking at every nth hit. So in this case, every 250th write to the frame buffer, we're writing a frame and then adding a delay. And this is actually just making a copy of the frame buffer memory and storing it in a queue. And then later we convert that into an RGB image and pass it to JavaScript. So for static binary translation, there are some things you just kind of can't really do statically. Like if you compute an address and then jump to that address, like you don't necessarily have the ability to compute where that's going to land. Sometimes you do, but in the general case, you really don't. So there are some places where I have to mark, okay, here's a dynamic jump. Here are all the potential places where that dynamic jump can land, and those have to be marked ahead of translation time. Do we have any of those here? That's what these are, patch dynamic branch. So there is a function pointer that can invoke one of these three functions. And so this is just specifically indicating that, saying like, this branch at this address can go to one of these three targets. And then we insert some code at runtime that checks whether the address is one of those three places, and if so, it goes to the right place. So it turns into, I think, a switch statement. More continuations. These are a bunch of places where I have to break up control flow. So it's like I've got a list of addresses that I just had to find by disassembling the code, and then it inserts a continuation at all those addresses. Yeah, and then there are some places where we're just substituting the original code for some of our own. So for example, this was a function that did a pretty low-level joystick pull where the hardware it was dealing with at the time had like a resistor capacitor timing circuit that was actually built around the potentiometer in the joystick. So you could charge it up and then measure how long it takes to discharge or vice versa. And so it has this timing loop that just uses the duration of the instructions to measure that particular capacitor charge for the x and the y axes, which is cute, but I'd really rather not emulate that. Like I could emulate that because the translator has a feature which I use for sound emulation, where if a subroutine makes any ISA input or output calls, so like IO, like in or out instructions, then it'll enable a flag which causes it to keep track of a cycle timestamp for every instruction in that function. And then when it calls the implementation of the in or out, it passes that timestamp in. So that's how we do audio. This game bit bangs, like it generates all of the sound effects by just kind of timing a loop that causes a little click, like an impulse on the speaker. Probably because it was ported from Apple II code, which did the same thing. I don't know if I still need this, actually, this patch video blit. Yeah, I don't know if we're even using these anymore, the video back buffer. This used to be part of the patch for implementing CGA graphics, but this is the new hotness, this patch video high level. So I think this is a Tuco related typo maybe. So yeah, patch video high level. Yeah, so there's a debug feature which is off by default that actually throws an exception anytime the binary writes to the back buffer, which is at this address. But normally we're inserting traces that replace entire functions with some C++ code. So we're finding the sprite drawing function, finding the addresses of all the arguments, then replacing it with some C++ code that reads the arguments, calls this drawSprite function. Similar thing with drawing playfield data, drawing text. So like the basic pattern here is doing some pattern matching to find the memory addresses we need, and then doing some pattern matching to replace the actual function with the right bits. 2 goes down here by my foot. Yeah, line drawing. All right, so we've got all that. That generates more code. So yeah, what is actually in here? So this is defining a class. Every exe file turns into an instance of this SBT process class, which is one of these. And in fact, the subclass has this declaration. So there's a macro which actually defines the subclass here. It'll have a constructor. It has a bunch of virtual methods like load environment, get data, data length, relocation, etc. Get function and get address are kind of interesting. That's how we actually publish entry points and publish data addresses that we can use externally. Yeah, actually I think everything goes through get function and get address now, like once the data segment's loaded. So that's the data image. This is a lightly compressed data image. It'll get gzipped as we transport it over the network later, but this has basically got all the zeros RLE compressed out at least. So it doesn't have giant fields of zeros. And a bunch of subroutine declarations. This is the region where the Python translator code can like add some extra C++ declarations, so that's something that was added by one of the patches. Yeah, and then we just got the actual translated functions here. So stuff like this where we're reading memory, anytime you are reading without changing the segment, like DS is a data segment, it's like a pointer that can only point to something that's a multiple of 16 bytes. So you can think of it as bits 4 through 19 of a 20-bit address. And so the way I translate those is kind of interesting. This g.s is, so g is globals, s is segments, and so that's actually a cache where we keep native pointers to the beginning of every segment. So we only have to do any kind of memory validation, because the virtual memory that this machine has is like 256K, so not all segment values are actually valid. There needs to be at least some kind of translation step to go between a segment pointer and what this program thinks of as native pointer, so something that's inside the WebAssembly heap. So that happens infrequently. It happens when we actually start running a particular entry point. It happens anytime the segment register is modified. But normally we can just use this native pointer or the WebAssembly native pointer as it exists. So then this would have been an offset in native code. So this shows up as data segment colon some offset. We're copying DL into it. So that just turns into copying something out of this register structure into an array that we get to via this DS pointer. So like, it's pretty straightforward translation for the most part. Some of these also update flags. The flag update mechanism is inspired by, what is it inspired by? So I've been doing this for a while, this thing where I don't compute the flags result right away. I feel like this is a trick I saw some other emulator do. I don't think I invented this, but it's like been a while and I can't remember where else I actually saw this. But maybe it was QEMU actually, because this is something I feel like I've just been doing this for a while, where instead of actually calculating the flags, it uses a larger register to store the result from the operation. So for example, if this was a 16-bit operation, you could do an addition in 32 bits and then store the result of an unsigned or assigned 32-bit operation. And then you can figure out later by looking at bits in those registers what the actual flags would have been. So that's what this stuff is about. This S result and U result are 32-bit values that are used as intermediates to calculate the flags that would have resulted from a 16-bit operation. You can do the same trick with 64-bit and 32-bit. Oh, I think I started doing this when I was working at Siftio. Like, the binary translator I built there was doing this. But maybe I did that. No, I did that after. I wrote this code before the binary translator, because I wrote a static binary translator at Siftio also, which uses a very similar technique, but that one I wrote based on the experience that went into this. So yeah, I don't know. It just seemed like a good idea. I like stealing ideas from myself. But yeah, maybe this did come from somewhere else. Because yeah, I think you can see the binary translator in Thundercracker, which is the Siftio codebase, doing something similar. That one has a binary translator that goes from 8051 code to C++. And so it's a little different. Instead of operating at a function granularity, that one operates per basic block. And it generates, I think, a function per basic block. And then big lookup tables with all the entry points for those basic blocks. Because that needed to do somewhat lower level translation. I couldn't rely on functions being well behaved in that code base. Okay, yeah, maybe it was QEMU. Yeah, I don't know. It seems like a good idea, doesn't it? Maybe it was somebody's ARM emulator. Because, I mean, there are a lot of challenges in getting the flags emulation working right and high performance, going from ARM to x86 especially. And I mean, I tried, I basically tried a few different things here, and I remember reading the disassembly, and at the time this was like what would now be a pretty ancient version of GCC, and I was mostly looking at the ARM code that it produced. But I remember trying a few different things, and in fact, trying different ways of storing the registers. So at first I thought it would be great if the registers were all actually stored as local variables with no pointer aliasing or anything else, to be really sure that the optimizer could do its best work with those register accesses. But then it just seemed like I couldn't escape the overhead of kind of copying registers unnecessarily, doing it that way. And so this way I'm not actually copying registers at all, but there's a lot of pointer aliasing. And so the generated code, if you look at that, has a lot of like loading addresses for the register base structure and stuff like that. But when I tried something else based on you know, storing registers locally and then passing them by value into and out of functions. I was hoping that the optimizer would be able to do at least some kind of like inner procedure optimization within the same file on those register structures, but it didn't really do much. Be interesting trying some of those experiments again on more modern compilers. Because I mean, right now this is going through LLVM, but like it's also a little bit weird because the output is WebAssembly, and WebAssembly is a weird target. Like the code that you get out of this is just strange because it's all like nested S expressions. It isn't a register machine; it's like a stack machine, so it's weird. So anyway, this code is just like a soup of functions. These functions can call each other directly. So this call, for example, turns directly into a C++ function call. So that turns into a native WebAssembly call. These stack operations are mostly for error checking. They're not really necessary. I could remove them if I wanted to be less able to catch errors, but the performance hasn't really been a problem lately. So that's like most of the game, but then entry points, like how do we even get into that code? That's what this is. So not all of these functions are published outside the file. We only actually export addresses for a few of them. There's an entry point. That's where the game actually starts. After we get to the main loop, then we're really dealing with continuation functions. So we have all these calls to continue from. Every time we get to a continue from, it stores a new continuation pointer, throws an exception, and then the next time we re-enter the game, we'll start back from like whatever this pointer was. So that's where we usually end up in practice as an entry point, but those aren't actually published. Those just end up being passed into continue from as function pointers. So we publish, save, and load entry points. You know, this is like a place where if we wanted to identify other functions like grab an object or disconnect a wire, utilities like that might be useful to export, and we could export pointers. We've got data pointers for sure. So anyway, that's usually not stuff we call directly. Engine.cpp is sort of the main file for the WebAssembly portion of this. And so it's actually declaring some processes and then attaching them to two different hardware environments. This is the main game here. There's actually another hardware environment. This is basically a memory buffer, so it's 256K of memory that the 16-bit code runs inside of. It's also a separate input and output queue. So this is effectively a separate instance of the game that we keep around for doing screenshots and stuff. Right now we're only using this for screenshots, but we could use it for other things. Oh yeah, I'll bite. Adler is asking for kind of a UR here. Yeah, so this is Robot Odyssey Rewired. It's a port of an old game, specifically Robot Odyssey from 1984. And you can try it out if you go to robotodyssey.rewired, or sorry, robotodyssey.online. Then you can play it right here. Yeah, I was getting a little sidetracked with going into some detail on how this kind of binary translation runtime works, but the main thing that I added kind of recently that I thought I'd go into a bit is this storage system. So if you go to load an existing game, you get this field of thumbnails. All of those files are stored in your browser in IndexedDB, and the thumbnails are generated from that stored data when you open this window. That's the new part. So yeah, I don't know. It's been nice, like, trying to make this a good experience. Like, I like how fast it loads. I like being able to store the files in the browser. You can drag files into it to import files. You can export files as a zip. Let's see if I can demonstrate that. So if you drag a directory full of chips in here, for example. Then it stores them. Load a chip. You'll always have the ability to load these built-in chips also. The game comes with a bunch of saved chips. And so previously those weren't really accessible. You would have had to upload them yourself from your own copy of the game. But now they're included in the file manager. So even if you start a brand new, so if I open this in a private browsing window, I have no saved files here, but I can still go through and load a built-in design into this chip if I want. So that's the stuff. So yeah, this engine runtime, we're actually attaching all of these processes to a hardware environment, which is sort of like a combination of a tiny emulated DOS and a tiny emulated memory manager, and just like a really little environment that the emulated code runs inside of. So that class looks like this. We have some entry points for emulated interrupts that take registers and a stack pointer. You can call exec, which is sort of the main entry point to get one of those processes started. So exec, just like resetting some of our internal state, finding the process, and then calling process exec, which is down here. Oh yeah, that's actually in this file, sbt86. So this file is like runtime support for the binary translator. So when you exec, this actually gets ready to run a new process. So it clears the registers. It decompresses the exe's data segment and clears memory. That's what all this stuff is doing, setting up the game's memory environment. This is a bit of like DOS nerdery, but it's setting up this thing called the program segment prefix, which is where the command line is stored. And that's important because we do need to be able to pass command line arguments to the game's binaries. And then after this point, everything's asynchronous. This default func and default reg and continue func and reg, those are used every time we enter the game. So that's what this SBT process run is going to do. And so we have load environment. Load environment is, it's like setting up those data segment caches, I think. Oh, that's right, yes. This is a virtual function that gets generated by the binary translator. So if you go to the generated code, load environment should actually set up these global variables, which are not accessible anywhere else. I tried to design it this way to limit the visibility of these variables to give the optimizer fewer aliasing concerns to worry about. I'm not sure how much it's helping with the current backend, but this seems like at least a good foundation to build more optimizable code on. But it's like maybe something to look closer at. So my theory here was that I want these values to have no like long-lived pointer aliases, so the compiler can make decisions about if it wants to change the layout in memory if it wants to. I don't think a C++ compiler would actually reorder these as a structure. A previous iteration of this had them as separate items in the data segment, but I ended up changing it around just because I wanted to try a different way of aliasing these within the local scope. I don't know, it's like an opportunity to try like playing with different ways of writing the code and optimizing it, and then looking at the generated assembly and seeing what makes it better. And I've done a bunch of that with the earlier ARM port and less of it with the current WebAssembly port. So yeah, load environment stores stuff from the stack and the registers locally. It's also setting up this segment cache. So So this S instance, that's one of these SBT segment cache. So yeah, this is how we actually load those native pointers. Memseg is like the main memory management entry point. You give this an emulated segment and it gives you a native segment. So an emulated segment is a 16-bit number that comes from just like any 16-bit code. And then this pointer here is a native pointer to the actual memory that underlies that segment. And it's guaranteed to have 64K of valid memory there. So once you've retrieved this pointer, you no longer have to do memory validation, as long as you don't reach further than 64K past the pointer. So just some utilities there. Yeah, the stack is very virtualized. This doesn't try to be a normal stack at all. This is, as it says, it's strongly typed. It's here mostly for catching errors. There are places where we have to store words or flags on the stack, so it also manages that. But mostly it's for error checking. And then here's emulated registers. So it's got unions. This is like a pretty classic way of representing DOS registers, or like 16-bit registers. Like you see it a lot in like 16-bit code written for DOS that has to represent. Like I think the first place I ran into this strategy was like Turbo C++, like writing code that calls DOS interrupts. I think I saw it in some book that was written for that compiler. Yeah, and then here we're actually calculating flags based on these values. In the relatively rare circumstance where we have to set the flags, we're modifying U result and or S result to accomplish that. This also does not emulate all of the flags, it only emulates the flags we need. This takes a lot of liberties with like corners cut in the x86 architecture based on what the game actually needs. So then the actual binary translator is mostly this one Python file, sbt86. So then this pretty much introduces it. So this isn't a general purpose binary translator. That wouldn't be possible because of self-modifying code and dynamic branches. So this uses fix-ups in separate Python modules that actually make each particular file translatable. Patches affect an analysis phase where we discover subroutines. Yeah, and so it makes it pretty easy to stub out dead code. So if you put a return instruction, it'll still follow where the instruction pointer would have gone if you didn't insert that patch and mark all that as code, so it won't get included in the data segment. But it won't actually generate code for it, because when it actually descends into that function, it'll hit the return and return. So yeah, 2009. Oh yeah, so there's like a lot of separate data structures in here. This is a table of clock cycles, because it needs to be as cycle accurate as it can for the audio to sound right. Memory addressing modes and data sizes. And so this isn't actually reading the machine code. This is reading the output of NASM's disassembler and disasm. That's why you won't really see it processing machine code here. The machine code patterns in the earlier stage, that's because that actually runs before the code is disassembled. So it can insert kind of textual assembly code, which is then processed the same way the text from ndisasm is processed. So then here's all the actual code generation. Warn self-modifying code. Yeah, so this is a little bit obtuse because there are some critical pieces of each function that have been separated out into shared utilities. So like this result shift thing, the U32s, oh yeah, this justifies flags properly for byte-wide operands. Where are we actually writing the results? I think this is the destination code gen with write mode. That's how it actually... Yeah, because there's a data type that represents an operand, and I think that actually handles the read or write. But anyway, like, you get the idea. There's code for each instruction. You've already seen like the overall structure where we're using gotos a lot to emulate control flow. Those end up getting turned back into loops and branches and or like ifs and whatever by the mscript and relooper. This is the dynamic branch code. This is where it actually generates a switch statement. So yeah, here we have jump bx. So this would have been looking at this register and then jumping to a location based on what's there. Yeah, that's interesting actually. I was talking about indirect calls, but indirect jumps are also supported. And in this case, these are within the same function, so they turn into labels. So this is a switch statement with a bunch of gotos that jumps elsewhere within the function, or to failed dynamic branch if it's not one of the values we expect. And then, yeah, file I/O and keyboard and everything else gets handled by C++ callouts like interrupt or the drawing functions we were seeing earlier. Here's a vertical line, for example. I don't know why the vertical line ended up getting translated into the middle of a function here. So here's a v-line by itself. It looks like there are a couple of other functions that ended up jumping into v-line, so we actually have an inlined copy of v-line. So yeah, EDA0 is the main copy, but then like over here in 1A978, it's inlined. It's fine, a little bit of code duplication. Yeah, totally. So like name table, if you want to file a GitHub issue, that would be helpful because like that's definitely an obvious improvement that would be useful, but yeah, it's just like having the ability to save files with different names would be useful. I've also been thinking about like the way to make the autosaves less giant in the listing, I think, might be to have a checkbox that's like show all autosaves that would be off by default, and then maybe without the checkbox it only it tries to take like. So I'm imagining you sort the files by time, and then if you have a contiguous run of autosaves, you only include the latest one. One reason I haven't done this yet is I'm not even actually sure whether this should be a UI feature or whether it should be part of the autosave engine in the first place. Like, it should be maybe that the rules for when autosaves get taken are slightly different, so that like maybe autosaves should be allowed to replace other autosaves that have occurred recently or within the same area of the game or something like that. So, so yeah, I'm thinking about how that might work. But yeah, that's a good suggestion for sure. Alright, so what does this look like from the engine side? So in main actually does not do very much. It really just sets up this loop. And the loop is not going to do very much on its own. So this has the opportunity to run periodically. If there's no process, so if process is null, then we actually pause the main loop and stop running this. If we do have a process, then we make some progress on the output queue, we make some progress on running the process, and once we have some delay that's larger than the minimum, then we'll actually ask for a callback. So once the WebAssembly loads, it has the opportunity to run processes, but it won't be doing anything until exec gets called, which sets up the process, resumes the main loop, and then we've just got a bunch of ways of getting memory and input in and out of the game. So, yeah, that was a bit rambling, but hopefully it explains a bit about how the binary translator works. This is a long Python file. This is like 2,000 lines in one file. This could definitely be split up a bunch. This is like the template for the generated C++ code. Alright. Well, let's go through some of the JavaScript file management code. I need another quick restroom break, but then, oh yeah, I never even actually went through all of this build output. We just got stuck on SBT86. So anyway, this might make more sense now. We're locating patch locations, patching them, doing the analysis, which is the part that actually takes a little while, generating the code, compiling the code, and then doing it all over again for a different exe file. So the original game was split up into multiple exe files so that it would be easier to fit it into RAM, as well as so that it could split across multiple floppy disks. But in this case, we can just lump all that back into the single WebAssembly. Show.exe is what used to be menu.exe, but during the patching was pretty extensive, and it moves the menu entirely elsewhere and just leaves the intro cutscene. I should debug these warnings. These are not actually real. This code that it thinks is self-modifying code is actually just some data that's been stored in the code segment. And I think I have annotations that say don't worry about it, but the annotations aren't working for some reason. So that's something I should deal with. More patching. Okay, and then there's all the code generation and patching done with. So now it's just compiling normal native code. So yeah, it compiles the tutorial, compiles like this engine. SBT86 is like runtime support for the binary translator. Then there's like input, game data, compression, output, drawing, etc. And then for some reason we're building this show file repacker. Oh yeah, I was expecting it to build the compression library, but I think that might actually be a bug in make clean, that make clean does not actually delete the library code that we build, because there's also a .a file over there in library/z standard that we're building, but I think that's already built in this case. So we would have been using emcc to build this compression library called zstd. That's already built. So now we're packing the show files. So yeah, this is where it decodes the data that menu.exe would have been reading for the menu and generates a bunch of PNGs. On the images, it's carving up the images into smaller images. And then we take some of the game's data files and pack them back into a C++ array thing that we use to get them out of the WebAssembly at runtime. But the game has some small data files that we do this to. So actually everything that's in this fs directory. So the built-in chips, the chips that are used for the game's levels, the tutorials, all of those end up as data files that get turned into a lump of C++ code right here. And an index. So yeah. And those turn into files that we can retrieve at runtime, either from JavaScript or from DOS. Oh wait, okay, no, there's Z standard. I don't know why it compiles Z standard after doing the show file repacker, but I guess that's what we got. Oh, I do now, because it was actually trying to compile fspack, but then that caused the make file to go run the dependency that unpacks the show file. So fspack, hardware, more C++ code, compiling static library. Then this is actually compiling the WebAssembly. So it's got a bunch of object files, it's got the compression static library, a handful of options for the WebAssembly generation, a bunch of verbose output. Okay, and then it's running this font to SVG script, which is, that's actually reading the original game font and generating vector outlines that we can then convert into a web font. But it doesn't actually generate the web font, that's done by Webpack. So then, that's all the stuff, everything above there, that's all the stuff the make file handles. Everything after this point is done by Webpack. There's the Webpack entry point. And that's generating icons and running HTML templates. And then that finally generates this nice distribution directory, which has our index.html. This file by itself has the splash screen, the font, the CSS, and the menu in it. The main JavaScript bundle is this file, and that contains pretty much everything else, all the JavaScript, really. There's one auxiliary JavaScript bundle which just has the zip file library. So if you upload a zip file, if you drag a zip file onto the web page and it stores it, or if you request the archive to download, then it'll dynamically load this file to get the zip support, but otherwise it doesn't need it. This is like almost as big as everything else put together. Yeah, and then the WebAssembly always loads, but it does so in the background, and it doesn't actually need the WebAssembly until you either open the file manager or load a save game, so we can usually defer the loading animation. And then SW is the service worker, and so that file actually has a list of hashes for the other resources. So this is basically a package of one version of the application that you can download. Index.html also has the version number in it down here. So yeah, I can speak in a little more detail about the storage system in a bit. I'm gonna hit the restroom again, but I'll be right back. Oh yeah, 2 goes like right there. Were you successfully tracking Tuco for just a second and then stopped? Oh, hey, Tuke. Winch number 1 does not have the most cylindrical of pulleys. I think it's one of the noisier winches here. Alright. So yeah, that's like the low-level stuff. If you're interested in exploring the source code, just again, this is on GitHub. Scanlime/Robot Odyssey Rewired. And yeah, I've tried to reorganize the source code so that it's like a little easier to deal with, although there's certainly stuff that needs work. For example, this game menu thing is just a big ugly state machine that manages all the kind of game state transitions. This definitely needs work. Some of it's cleaner than others. Yeah, I don't know. I just did a big refactor that made some improvements at least, but it certainly needs more. So here's the main entry point. Oh, that's interesting. Nametable asks if I've tested plugging a gamepad into a phone or tablet to play in. They've tried it and it appears to work. I can't say I do. I don't have. That's actually. I wonder if I do. I don't know if I have an on-the-go adapter handy. I should check. I've got one kind of old Android phone that I use for testing, and it might work on there. I've got a Bluetooth LE gamepad that does work with iOS, and I've been testing that pretty regularly. But yeah, I haven't tried plugging a USB gamepad directly into an Android phone. I'll have to try that. I didn't know that that worked. But yeah, Bluetooth LE gamepads are definitely a thing that this should support. But yeah, good to know. Oh, that's a good question. Weebrew Lover asks how I extracted all the game's resources, if I hadn't answered this already. Yeah, there was like a whole stream on that, so like if you want a ton of detail, then I might refer you to that entire stream on it, but I will definitely give you a quick look through it right now, because there's definitely a short answer.
You hungry?
Oh, geez, thank you. Whoa.
If that's too much, I can take one.
No, this is great. I could definitely eat this much. Thank you. Oh my gosh. My friend just came back from a walk and brought me pizza, and oh my gosh. Oh my gosh, this is amazing. I'm gonna take a bite. I shouldn't stream like super too much longer, but yeah, I'm happy to answer questions about how this works, and I would like to at least go into some of the storage stuff a little bit. Put this down until it's a little bit less enormously hot. Where did Tuco go? Let's put the camera right there. Well, Tuco might wander for just a bit. Let's see. So the game actually has files in various different formats. So first stop should be checkoriginals.py, since this is what actually checks the original game assets. The original directory here will instruct you to put the game files here, but these aren't actually in the repository. So you'll have to obtain the game yourself and stick it in this directory. And then this will start processing it. So yeah, this will just take an input directory and an output directory, and it'll just recursively extract everything, unzip everything, and in the pile of files that it ends up with, it'll ignore the names even, and it'll just take the hashes and look for these particular hashes. So it looks for the EXEs. These EXEs actually have a decent amount of game data in them, but it's, you know, it's like in the form of like data tables and code and stuff that is just like not very structured. So like these definitely have stuff that is more than just like an engine. It's definitely like per room and per object kind of stuff in there, but it's just like piles of code. Like it's not really any kind of structured data. There is, however, a whole layer of structured stuff that happens under that, where there are rooms and sprites and objects and that kind of stuff, and circuits, and those data bits are stored in this world file as well as the circuit file. These also turn into part of the saved game. So like the saved game is actually bigger than some of these data files. Like the saved game would be basically the equivalent of the world file, the circuit file, all of the chips that you have loaded at the time. So like these file formats are all kind of interrelated, but you know, like they kind of represent different chunks of memory that the game deals with. And so world, this WOR, is if you go into the game's JavaScript console and look at the world data, it's like 15 kilobytes or something. That's this file, just that's all it is. A circuit is kind of right after that in the save game file, but it's distinct in memory when the game's running. So anyway, the world file includes playfield data, it includes all the sprites. I don't think it includes objects that are drawn separately, like the sentries in the game. I think the sentries are actually in the exe files. I think the walk cycle is in the exe files, because the walk cycle is actually dynamically patched into the sprites as you walk. But most of the in-game objects are in these. And so during the process of reverse engineering the game's save file format and the world format, I figured out like the graphics in there. But then there's also a font file, which has a separate format, this font.fon. It is just like a very, very low level, very raw 768 byte file that includes a bitmap for every character in kind of a weird order. But so those are pretty straightforward. The one that we're getting all the menu graphics from, which is probably what you're actually asking about, is the .show file. And so that's what we unpack into this extra directory, show. Pizza. So this actually passes those off to showfile repacker. And this Python script actually documents the format we're dealing with. So it's, the whole file is just this one format. They're either end of frame markers, RLE compression. So this is a really simple type of compression that has the ability to repeat bytes or skip regions of memory. And that's all it knows how to do. So we're separating these individual frames out into PNG files, writing them to disk, taking the frames we still want, recombining them. That's what we got there. Oh, that's another good question. Adler's wondering if the whole process of porting the game was streamed. Not the whole process, because I did start this back in 2009, and I definitely wasn't streaming any of that. But I've been doing a lot of this on stream. I think lately I've been, doing streams every so often where I'll do a bunch of work on stream, and then I'll be doing some work in between streams. And the ratio of stuff that I do on screen to off screen has kind of fluctuated. There was a stretch for a while where I was doing pretty much all of this on stream, but yeah, so you won't find the entire development process on my YouTube archives, but you'll find a lot of it. And yeah, I have all the archives on Twitch and, I have all the archives on YouTube and as much as Twitch will store on Twitch. So Twitch doesn't store archives indefinitely. You'll find, I think, the last few months of streams on Twitch but older stuff will all be on my YouTube scanlime-in-progress channel. Yeah, this is where we're actually taking the kind of cutscene data and extracting just the portions that we're using for the menu. These are actually the heights of the different sections of the main menu in pixels. So anyway, let's look at the storage code a little bit. So if we step outside the engine and just look at the main kind of JavaScript and CSS and HTML land over here, let's see, we've got a few directories that are all JavaScript code. Well, so assets here, some of this is JavaScript, but this is all stuff that's run at build time. So like this font to glyph, or sorry, font to SVG, this is actually processing the game's font file, generating outlines using this region 2D library, and then converting that to SVGs using this chunk of code here. But if we ignore the assets directory, then like this is the stuff that's actually at runtime. So there's a main entry point. The pattern here is that I have a bunch of separate modules that communicate mostly through just like module level imports, but then there's a specific sequence that they get their init function called in. So engine loader actually starts loading the engine in the background, and then it provides a promise that you can use to get notified when the engine's actually ready. There are a bunch of subsystems that usually have something they can do right away, but then something else they can do once the engine's actually finished. So let's just take a look at storage first. So storage comes from files/storage.js. So this is not that big, it's like under 300 lines. So init, this is using a really thin wrapper around IndexedDB called IDB here, which just changes the API a little bit to use promises instead of separate callbacks. So it's a little easier to deal with in ES6 with async and await and all that. So this actually sets up an asynchronous request to open the database and passes that along to these two objects. And so the objects get created immediately and attached to the engine so that they can be located by other objects. But the database won't necessarily be ready yet, and we're actually just going to hold on to that promise and keep it around for later so that we can queue up kind of arbitrary operations against a database which may in the future become available. Similarly, we want to get those static files, so these are chips that are built into the game bundle, as well as other files, but we're mostly interested in chips. And that has to wait on the engine to load. So for example, this is an asynchronous function we're calling. This is waiting on this promise that the engine loader puts out. So this will kind of stall, it'll come back after this line once the engine's done with a value here, and then we can call this C++ function, which is up in here, get static files. And this is using the Mscripton API to generate JavaScript objects from the C++ side. So it's iterating over the native C++ file objects, generating JavaScript objects for each one with getFile, and then returning a dictionary, like a JavaScript object of those files. So yeah, then we have these settings and files objects, which are just different ways of using this database to accomplish something. Start with settings because it's actually pretty simple. Settings is basically a key value store. I could have used HTML local storage for this, but IndexedDB is theoretically higher performance than local storage because you never have to block the main UI thread on I/O operations. So even for settings where it doesn't matter that much, it seemed like it would be nice to use IndexedDB instead of the older, slower interface, which was HTML local storage. although it might be useful to look at the database schema. So yeah, IndexedDB is interesting. This project was basically my excuse to learn some things about IndexedDB. It is a key value store, but you can set up additional indices on those values, and the values are JavaScript objects. So in the simplest form, you can create one object store, which is what we've done with settings. And in this case, the key is something which is inside your object that you're storing. So the object itself is going to have a member called setting, which indicates which setting we're storing. The API also supports storing keys outside of the object with out-of-line keys, but this seems to be a convenient pattern. So this is a pretty simple object store. The files object store starts out pretty much the same way. We just have a different name for the key. But then we add some additional indices so that if we store files, we can also refer to them by their extension or by their date. In this case, I think the first parameter here is the name of the index, and the second parameter is the key path. And so this would be kind of as you expect. You could like have, if this was like some kind of nested object, you could say like filename.extension.string or something if you had something more complicated. But in this case, it's just a single member. And so IndexedDB fairly conveniently actually manages the database versions for us. So this is just a number that we've chosen. It doesn't have any real meaning except that it needs to monotonically increase. So we could jump by any increment we wanted, although it would make sense to jump by 1 every time you make a change. So for example, if I wanted to change the database schema so that it stores an index on settings, like let's say I want like a timestamp on the setting, and then I want to store an index so that I can sort like which settings have been changed most recently. If I wanted to make that change, I could bump the version to 2, and then upgrade database, in addition to being called when the database is first created, it gets called when you open the new version of this app on a browser that has the old data. You get an opportunity to make that schema change and add the additional index or additional object store or change your data's format or whatever. So I haven't done that yet. There actually already has been one format change, but I've chosen to do that as I encounter each record rather than on the entire database. So yeah, the settings store, you can create this anytime, even before the database is ready, as long as you give it a promise that will eventually resolve to a database. And then we're extending that with this additional promise that resolves to the database's initial settings content. These databases use a cursor, which might be a familiar concept from like other database APIs, to point to a current row in the object store. Like if you're used to SQL or SQL, however you want to say it, if you run a query in SQL, it'll give you a bunch of rows, and then you can point a cursor at the first row and then kind of march through them until you've read them all from the database. That gives you a way of kind of abstracting this concept that the database should go run the query, store the result somewhere intermediate, and then give you the ability to stream the results back to your application, not just like load them all into memory in one blob and retrieve them all at once. So it's like a streaming API for data. And in this case, the way IndexedDB implements that is by calling callbacks on a cursor object repeatedly until you've exhausted the available data, and then it gives you a null cursor. This particular IndexedDB wrapper for promises, it looks slightly different in that it gives you a promise for the transaction itself, but then a callback for each iteration of the cursor. But then, just like if you were using plain vanilla IndexedDB, you'd be checking the cursor for null and calling continue if you still want data. So this is an opportunity for, for the underlying database to retrieve like a block of data from the disk and then maybe immediately complete all of the kind of cursor requests that can be satisfied by that block of data on the disk, and then maybe make you wait once you march past that onto something that actually has to be fetched from the underlying media again. But in this case, for settings, like I just want everything to be loaded into memory right away because they tend to be important, and I want this watcher, which we're going to see in a sec, when you watch a setting, I want that to be called with the initial value no matter what the setting is. So, yeah, and then this is just like a basic like observer pattern. So there's a list of functions. You can call watch to get notified when some data changes. If we already know the initial value, we call the callback immediately. Otherwise, you get notified when the initial settings come in through the cursor here. And then we also call the watch function if you modify the value. So watch doesn't have any IndexedDB stuff, it's just reading from the cache. But if you want to write, then it writes through to the underlying database. So we're, oh, you know what? I just noticed that we're not actually saving this to the cache. That's a mistake. We're calling the watcher function. We're writing it through to the underlying database, but we should also be saying this.values key equals obj. That's a bug. Okay, we can make sure that compiles in a bit. Yeah, so that's the settings. Files are slightly more complicated. By the way, this is like the most object-oriented code in this whole project, basically. A lot of this stuff is just like piles of procedural functions right now. Mostly because I haven't entirely... Like, when I started writing this, I wasn't really sure what should be considered part of the engine object versus what shouldn't. And I've had some competing constraints there. Some things need to be accessible from the WebAssembly side, some things need to be accessible from the JavaScript side, some things I want to be accessible from like the debug console. So it's a bit of a mess right now, and it definitely needs some refactoring. But yeah, similarly to settings, you can start up this files object, and it just needs a promise for when it will eventually get the database, when it will eventually get the files from the engine. You can save. This is an async function. This was one of the gnarlier functions before I started using async, because I originally wrote this using plain vanilla promises, and that was kind of annoying, but async makes this much nicer. So I'm making a copy of the data. This also truncates off the whole rest of the WebAssembly memory space and gives me just the save game, which is nice. Ignoring hidden files, extracting zip files. This is where we actually asynchronously import the zip library. So this is that extra bundle that we don't always load. Only if we find a zip file we load this. But yeah, so like we're ignoring files that are too big, we're extracting zip files and recursively saving the individual files in the zip file. And once it comes down to the individual files, we're making this object. The embedded name here happens to be the primary key, but we also have indices on the date and the extension. I'm not using the extension index yet, but you could use it, for example, to just list the files that are, like, only list autosaves, or only list uncompressed saves, or only list chips. I'm not doing that right now. IndexedDB doesn't have a query language built in, so you can read an index, you can read part of an index, you can read the index forward or backwards, you can start in the middle of an index and read forward and backwards, whatever. But you can't take multiple indices and then do a join and look at only the rows that intersect. Like, if you want to do that, you'll have to basically do the same thing that the SQL implementation would be doing itself, and make some decisions about which index you want to iterate over, and then like do the filtering yourself in that index. So there are some higher level database libraries that'll do that kind of thing on top of IndexedDB, but for this I don't really need something like that. I might change my mind at some point, like depending on how complicated the filtering in the UI wants to get. Maybe we do end up wanting queries, but right now this is just using plain vanilla IndexedDB. So you have to open a transaction specifically with read or write mode, and then a list of object stores you're going to be operating on. And then everything you do inside that transaction is an atomic operation. The whole thing completes, or the whole thing doesn't complete. The end of the transaction is a bit implicit. Transactions end automatically when the JavaScript runtime is between event loop iterations. So you open the transaction, you do a bunch of stuff with it, reading or writing, and then after you return to the JavaScript event loop, then that's when the transaction completes, and you get a notification. So you can't really hold transactions open for long periods of time. They kind of automatically close, which is an interesting... Like, it seems to work pretty well. I've just never seen a database that works like this, so it's kind of neat. So yeah, higher level save functions. Yeah, and then listing. This is currently the only way we have of listing the files, and it's iterating by date using the date index. So if this was the only way we ever wanted to store files, we actually wouldn't need any indices. We could just use the date as the primary key. But I like the name being the primary key because that makes it easy to replace files that have the same name, and it makes it easy to use that as the uniqueness guarantee. So that's like the primary key for the object. So it does make sense to have that be the primary key and then a separate index for date. But yeah, because of the lack of joins, if you want to sort by date and then filter by a certain extension, the way I'm implementing that right now is to use the date index to do the sorting and then filter it after we have retrieved the value from the cursor. So we're filtering out hidden files, and then we have the opportunity to do some additional filtering after this list files returns. So this tries to load as little data as possible. It'll only load does it load? So the date actually, yeah, this is nice. So I'm using a key cursor. Because of the way key cursors work in IndexedDB, it's not going to give me the value. It'll only give me the key, which in this case is the date because I'm using the date index. But because this is an index, it also needs the primary key, which is how you refer back to the indexed object. So because of that, I'm actually getting the date and the name as part of the cursor already without another trip to the database. So I've got that, and I can use getExtension to just extract the extension from the name. That doesn't require another trip to the database. And then I can make this kind of dehydrated file object, which doesn't have the file data, it only has the metadata, and then give it a closure that loads the rest of the data. So then load file is this thing down here that uses a different transaction to get the data by the primary key. This is a bit of a hack to upgrade objects that were in an old format, but for the most part this is not necessary. So we're getting the file in one transaction, then we're caching it, giving it a loader which just returns a copy of itself, or a reference to itself. So yeah, I thought that was kind of a nice way to just get a list of files, all of which have their metadata, but then you can load the individual contents lazily. And so that's how screenshots work. They only load data and then render a screenshot for the save games that are actually visible. Create zip. This is for making zip archives. This, again, asynchronously imports the zip library because it's huge. Then iterates over all the files, stores them all in the zip. This iterates over the main cursor, actually, not the index. That's pretty much all there is to it. Thumbnails are kind of interesting. So yeah, file manager. This open async function is what actually starts the file manager, and it gets this mode is how we distinguish between whether we're opening games or labs or chips, and that activates different parts of the UI. And the next state is just like where we go when we close. This code is still a little bit weird. It's got this kind of strange mixture of promise constructor and then and await. The reason I wanted to do this was I wanted to wait until we have any files and then resolve this promise. So this result indicates, as the comment says, whether or not we successfully found any files that match this mode. So we need that in order to open either the file manager or go directly to the game in case you don't have any files. But if there are no files, we actually still have to get to the point where we've seen the end of the cursor and know that we don't have any. So resolving this with false actually requires getting all the way to the end of this closure, listing the files, iterating through the list by getting this called for each file, and then finishing with that and then resolving with false. But if we find any matching files, so we're iterating, we check the file against the filter for this mode. That's a closure that indicates which files we like for each mode. If it matches the filter, then we call resolve with true right away, and in promises, the first resolve wins, future resolves are ignored. So as soon as we have one file, we can resolve this and unblock the rest of this async function, which actually, yeah, so this await here waits for either of these resolves, and then based on the result, we either activate this modal or we don't. If we return false, it's the caller's responsibility to go somewhere else, to some other state. This pause stuff is also kind of hacky. I think that there should be a separation between speed control and pausing because you're not in the exec state, but right now there isn't. Yeah, so that loads the UI. File view is what actually sets up each individual file. For the most part, we're not creating dynamic DOM elements. Like the HTML is pretty much all static in the HTML file, but we do populate these files divs with files at load time. So based on the file mode, we stick all the matching files inside this div. And so that's what this file view does. We're just creating a bunch of DOM elements the straightforward, ugly way. Setting up a click handler. And most of this is pretty straightforward. Like, we're formatting the date. We're like adding some CSS classes to style it. The thumbnail goes directly to this lazy screenshot module, which gets the HTML element, which in this case is an image, and the file reference, which may or may not have any data. It's probably just the file metadata and a closure that lets us load the file later. So then lazy screenshot is pretty self-contained. I think that's, yeah, it's only got these two exports. It's got add and disconnect. Disconnect just kind of like cancels everything, and add adds a single lazy screenshot to the queue. So this bit is a bit messy. I don't actually know of a cleaner way of doing this right now, but I'm holding on to a reference to this object, this data object, in the element. So I'm like decorating the element with this underscore screenshot data. And that's because I'm getting a callback via this intersection observer. But it has one global callback for all the elements that it observes. And so this is a relatively recent browser technology, which isn't in all the browsers I care about even. I think Safari is still missing it, but I've got a pretty good polyfill loaded for this, which is what you see up here. And so if the browser doesn't support it, it'll insert a JavaScript implementation, which isn't perfect, but is plenty good enough for my needs. And what that does, it'll give me a callback anytime an observed element intersects with this root. So this just happens to be the modal root for the entire dialog box. So anytime something scrolls into view, I'll get a callback with a list of observer entries here. And if that indicates that the entry is intersecting rather than like the intersection is ended, because this is a change callback, anytime it is intersecting, we can stop observing it and say that the thumbnail is now visible. So we no longer have to observe it. We've now just converted this from a kind of ignored potential future thumbnail to a thumbnail we are now actively trying to load. And the first step is to send out a promise to load this, do an asynchronous operation, get a promise for when this will be available from IndexedDB, and then wait on that promise. So once we finish waiting, we have this loaded file, which has actually got the data in memory, ready to screenshot or load into the game engine. And then we also need the engine to be loaded. So just in case the engine is still not loaded, we wait for it, but it's almost always going to be loaded by this point. And then we add it to this stack of elements that need to be rendered, and we start calling this renderer every frame. So as long as there are any elements in this stack, every frame we come through and do one screenshot. It would be optimal, or at least less bad, to do these screenshots on a background thread. But right now the problem is there isn't really an efficient way of getting a copy of the engine to the background thread. We'd have to load it all over again. So until more browsers support WebAssembly structured clone, this is my approach. Maybe in the future when you can pass loaded WebAssembly modules to a worker thread efficiently, it'll make more sense to do it in a background thread. But right now I'm just rendering one of these on the UI thread every frame. So screenshots the save file. This gives you an image data, which I'm using the canvas to compress and store in a data URL. At first, I was using a separate canvas for each thumbnail and drawing directly onto the canvas, but the problem with that is that you get lower quality scaling, because I think the browser is optimizing for interactive use cases where you might be updating the image a lot, and it's giving you bilinear downscaling, whereas if you convert this to an image and then insert like a source attribute in the image element, it'll actually give you the highest quality at I keep trying to say downscaling and downsampling at the same time. It'll give you the highest quality downsampling that the browser has available. So, for example, instead of just examining 4 pixels for every output pixel, it'll examine like a whole region of pixels, which works much better for these tiny thumbnails. So, anyway, I think that's like all the code I feel like rambling about at the moment. Nice. RW Krem says, "We've come for your dead code." Yeah, if you've got a dead code reaper, I've probably got a few bits that you can have. Yeah, didn't we find one earlier on this stream that I was like, I'll fix this later, and now I've forgotten where it was. File actions file has basically the handlers that handle like uploads and downloads and that kind of thing, but a lot of them are accessible as methods on this engine method or engine object, mostly so that I can call them from the JavaScript console. Because stuff like this, download RAM snapshot, there's no UI for that. I just wanted to be able to call it from the console. Yeah. Well, I think this is about it. I should wrap up the stream, but thanks so much for joining. I think this is basically my like milestone that I'd been sprinting trying to achieve with the robot game port. So I have a big backlog of other stuff to stream, and maybe I can do some of that tomorrow. I've got a couple of bold port kits here. I got a big package at the PO box last week, so I have no idea what's in it. We might be able to find out tomorrow. Yeah, if this is interesting to you, yeah, check out the code, play it, file bugs on the GitHub issue tracker. All that kind of stuff would be helpful. If you just want other stuff, then I'll be back with other stuff tomorrow, or probably tomorrow. So yeah, and a big thanks to everyone who supports the stream, sending in stuff to take apart, sharing this stuff with your friends, even just like giving me some feedback on what you find interesting and you know, what directions you would prefer the stream and the edited videos to go in, that stuff is super useful. And I'll keep, sending out cat pictures, especially for the Patreon folks. So yeah, thanks so much, and happy hacking. I'll see you folks next time.